Okay, let's get started. So to get us oriented, I really would be remiss if I didn't mention that phosphogypsum production is not the only harmful step in the process when it comes to making phosphate fertilizers. It really begins at the mining stage. It's a 4-part process that begins 60 feet below the earth in open pit strip mines. In Florida alone, over 475,000 acres of these of land has been destroyed this way. That land is never restored. It's only reclaimed at best. And we know that biodiversity never returns to previous levels before that mining occurred. Then we move on to the beneficiation stage, where that ore is separated from a clay and sand mixture that produces radioactive clay slime areas that the industry has sort of rebranded into calling clay settling areas. Also devastating. Then finally, we move to phosphoric acid and phosphogypsum production, which is the third step in the process. And this is all for a final product that we know causes harmful algal blooms and fertilizer runoff issues, nutrient pollution, hypoxia, the Gulf Dead Zone. So, but for today, each of those is deserving of its own workshop. But for today, we're just going to be focusing on that third step in the process, which is phosphogypsum production. Here's a typical phosphoric acid production facility, phosphoric acid being the main feed product in final fertilizer product production. And here is a sort of formula for how that is produced. We start with that beneficiated phosphate rock, which was beneficiated in a process using proprietary chemicals that we don't even know the chemical makeup of. But finally, we get that rock, which is slurried or transported by rail to a phosphogypsum or a phosphate fertilizer facility. That rock is then added to sulfuric acid, and that acidification process leads to calcium sulfate, which is the chemical name for phosphogypsum, a poisonous gas known as hydrogen fluoride, and then finally our product that the fertilizer industry is after, phosphoric acid. Later, at a downstream operation, ammonia is added to that phosphoric acid, and we get monoammonium phosphate and diammonium phosphate, which are fertilizer products. You can see that poison gas is then scrubbed. It's a harmful air pollutant regulated under the Clean Air Act, so it's required to be scrubbed. And we get fluorosilicic acid from that process. The fertilizer industry then sells that to municipalities for water fluoridation. And whatever they do not sell also ends up in phosphogypsum stacks in that pond water on the top that you see there. So that process creates 5 tons of radioactive phosphogypsum for every 1 ton of phosphoric acid product. We're talking large volumes of waste, 46 million tons per year. And why is that phosphogypsum radioactive? The norm, the naturally occurring radioactive material from the phosphate rock, has its own radioactivity. Now, when we say naturally occurring, that doesn't mean it's harmless. It's harmless when it's 60 feet below the ground where it belongs. When we bring that up to the surface, we're redistributing that radioactivity into places it no longer belongs. Again, part of why that land is so hard to reclaim in a way that's safe. Depending on the quality of the phosphate rock, the chemical reaction also concentrates the radioactivity in the rock by a factor of 60. And that transfers that radioactivity into the phosphogypsum waste, which is now no longer a norm waste, but a technologically enhanced norm. So what kind of radionuclides do we have? We have many, but the most concerning of which I've highlighted here is radium-226, the most abundant. It's a decay product of uranium. And the average in the United States, or in Florida at least, where the most phosphogypsum is produced, is 35 picocuries per gram. For reference, background soils have 0.5 to 1 picocurie per gram. That's the average of a background soil. So this is not merely slightly radioactive. There is no safe level of radioactivity. This is pretty radioactive stuff that we're dealing with. Radium-226 has a half-life of 1,600 years, meaning that by the year 3,260, there would still be half of it left. And it usually takes about 20 half-lives for radium to decay all the way, meaning we're going to be dealing with these radioactive phosphogypsum stacks for at least 32,000 years. Other toxic constituents listed in Appendix 8 to the hazardous waste regulations are contained within phosphogypsum. They include arsenic, lead, nickel, cadmium, chromium, silver, antimony, copper, mercury, and thallium. Also very large amounts of fluoride, because phosphate rock is about 2 to 4% fluoride. That's released by that acidulation process. Most of these are toxic heavy metals, either known or probable carcinogens. So what is this doing to our health? We really don't know what it's doing to residential people that live near the stacks, but we do know that phosphate worker mortality has been studied in a cohort, a long-term study, because a lot of these diseases have a long latency, and the mortality due to all causes was increased, including lung cancer and leukemia, in this long-term study of phosphate production workers. We would like to see similar epidemiological studies in the phosphogypsum, in the communities surrounding phosphogypsums. We don't have those yet, and that's a data gap based on misdirected science from the industry. In Florida, for instance, we have the Florida Institute of Phosphate Research, which is funded by the state severance tax on phosphate mined, and the majority of their studies go to looking at alternative uses of phosphogypsum that have already been banned by the EPA because phosphogypsum is too radioactive. So what's wrong with the stacks that we have? We have over 70 of them scattered throughout the United States, mainly in Florida, Louisiana, North Carolina, and Idaho. But in particularly in Florida, we have a sinkhole problem here. You can see the number of subsidence reports that Florida has had, and highlighted in the middle is a sinkhole that's happened under a stack. We've had 5 of those in the state of Florida underneath stacks, only 3 of which have been reported. So here's the first one in 1994 at New Wales, releasing millions of gallons of toxic processed water into the Floridan aquifer, which is the drinking water source for 10 million people. And then, of course, the 2016 sinkhole, which released 215 million gallons of processed water directly into the Floridan aquifer. That waste is still trying to be recovered by the company that owned that stack, Mosaic. They're currently pumping 44 gallons per minute to this day, 4 years later, out of their recovery wells in an attempt to contain that waste within their zone of capture, which is supposed to be on their property boundary. Now, whether or not that recovery is even possible is really unknown. There's a lot we don't know about our aquifer system. It's a complex karst geological formation with lots of fast-moving conduits. But we do know that studies have shown that the fate of that processed water and the fate and transport of that processed water is unknown. So it's likely it could possibly be reaching people's wells. We simply just don't know where that processed water has really all gone. Then there are 2 other sinkholes that happened in 2004 and 2013. These were not reported to the public. Public records request turned these up. So this is a schematic representation of one that happened in 2004. The industry called this an anomaly, but geologists say that has the functional equivalent of a sinkhole. Again, another processed water loss incident. And here we have a same thing happening in 2013. Again, not reported to the public. So what's happening is these stacks have gotten too large as the industry, which was once 30 different fertilizer industries, has now consolidated to really 3 main fertilizer companies, those being Mosaic Fertilizer, J.R. Simplot in Idaho and Wyoming, and then Nutrien, which was formerly PCS, in North Carolina and North Florida, and also Louisiana. Since they're so large, and especially in Louisiana, they're in Louisiana, which has weak clay soils, though that pile is shifting. So we're at risk of losing hundreds of millions, if not 1 billion gallons of processed water, because that pile was built too high, too large, even though EPA recognized back in 1990 that stacks in Louisiana should not be larger than 12 meters high. We're also subject to climate change and hurricanes and sea level rise. Here is the Riverview stack in 2004 had not even a direct hit, but high winds and rain eroded a berm atop the Riverview stack and sent 65 million gallons of processed water into Hillsborough Bay, caused documented death and injury to numerous estuarine species, caused a lot of die-off of mangroves, tidal marsh, and seagrass. Here's where that Riverview stack is located, and as you can see, this hurricane didn't even it came from the east. Riverview is on the west coast of Florida and still was able to cause that much damage. So when we do get that direct hit, and every time a hurricane enters the Gulf, I hold my breath because so many of our phosphogypsum stacks are located on the Gulf, out of convenience to the industry to both ship ore and fertilizer back and forth between the ports of Louisiana and Florida. Then there's just sea level rise by itself. So here is the Mississippi phosphate stack. There are 2 stacks there that are now constitute a Superfund site. Within some even moderate sea level rise scenarios, we start to see inundation. And then at the 6-foot scenario, we see definite inundation there. It's even worse in Florida on the Gulf Coast. This is again the Riverview stacks. It's already below the mean high water line, but with just 1 foot of sea level rise, we begin to see inundation, and that's not accounting for storm surge and hurricanes that are coming. Here's a picture of the Riverview stack. This stack is purportedly closed. You can tell that a stack is closed when it has that vegetative cover on the side, but yet it still has that pond because we like to use our closed stacks here in Florida, and that pond is still holding toxic radioactive process wastewater as part of the active stack system. And that arrow is pointing to Tampa Bay, just so you can see how close this stack is to Tampa Bay. Here's a neighborhood in Riverview built a few hundred yards from the active stack. These are also an environmental justice issue. So, for example, Progress Village, which you can see on this map right next to the active stack, was designed in the 1950s as a means to provide homeownership to displaced Black residents from Tampa and the construction of the I-275 highway. It was great while it lasted, and then a few decades later, in 1984, county commissioners approved a phosphogypsum stack just a few hundred yards away. The company at the time, Gardenier, established a sort of many beautification projects, a scholarship fund, things that really are a drop in the bucket compared to having to live next to a radioactive phosphogypsum stack and dealing with the dust that's blowing off. I've walked through that neighborhood. I've seen the dust myself. Dust in Florida and Louisiana and the Southeast in general is not as big of an issue as it is out west, and we're going to hear later from somebody who lives out west in Idaho. Dust there is a significant problem, A, because the climate is different, and B, because the process and the ore is slightly different. And with that, I'm going to hand it over to Matt Rhoda over at Healthy Gulf to talk about, to introduce our speakers that live in these communities.